All right, class, we're gonna get started. Yes, yeah, presumably one of the exams you have today is why people aren't here, I guess. All right, some announcements before we get moving. Last chance to sign up for CFD project teams is basically now. So I think you can do this on your phone if you need to as well. I will be making the teams after class and then sending them out to you all. I'll assume that if you didn't fill out the form, as of last night when I checked, there were a good number of you who hadn't, maybe half of you who hadn't. I'll assume that you're okay with whatever teams I make. And if you give me complete teams of 4 to 5, and I don't see any conflicts with like other people, who've submitted team requests, whose names you put down, then I'll go with those teams. So if you want, to know exactly what team you're working on, that's really important to you, then give me complete teams and I'll use them. No homework, so related to that, no homework this week, but the CFD tutorial will be due next Wednesday, and I'll be going through that material and updating the material on that assignment, just making sure it's all up to date today. Just note, I'm grading the exams now. If you don't know where to start, don't just write the Bernoulli equation, please. Okay. Yeah, don't do that. I know it's tempting, right? We talked about how Bernoulli equation can be tempting because a lot of times you're given, a few different parameters, like you might be given pressures and you're asked to find pressures and elevations and you're asked to find velocities. And Bernoulli equation relates all of those things together. But if you have a pipe in there and you have substantial friction within that pipe, then it's going to be more appropriate to use an energy balance. Yeah. Yeah, we'll call it the energy balance, and you can definitely write the energy balance. So Bernoulli equation with head loss due to friction would be energy balance, right? I'm calling it that to keep it distinct in your mind, because energy balance is more descriptive than Bernoulli equation with head loss, okay? Energy balance states that, so they both mean the same thing, right? Bernoulli equation with head loss versus energy balance with head loss are both the same thing. But energy equation with head loss is more descriptive because what you're really stating when you write that equation is a statement of energy balance, energy in and energy out of the system, okay? So that's why the nomenclature thing, okay? But yeah, anyway, don't just blindly start with the Bernoulli equation. I only add points to the exam. I don't take points away. If you notice on the grading, it's all positive. But if I could take points away for this, somehow I would. Anyway, just don't do this. Okay. Yeah. I'm about halfway done right now. So yeah. I mean, when I don't have like another major thing due at the same time, I try to get through it. Sooner than that, I think, is my goal. But I'm not going to promise something I can't keep. So, but you'll get them back when you get them back. I'll just say that. Okay. Any questions on any of this or other material or things we've covered so far? Okay. And so as I promised on Monday, there are some changes to the schedule coming, including some guest lectures next week. So we have Kevin Whitty is going to be giving a presentation on Aspen and basically how to solve pipe flow problems, simple pipe flow problems with Aspen. But once you know how to solve some simpler problems, then you could start building up networks and using tools to do that. On Wednesday of next week, your TAs will be going over some information about CFD and really to help set you up for the next phase in the project, where you'll be writing reports on your CFD simulations. So, all right, any questions before we get started? Okay, so to pick up where we left off on Monday, we were talking about boundary layers, and we said that when we're considering flow, external flow near a solid object, we are going to have this region that is close to the surface of the solid object, in which the viscous stresses are going to be important, right? And that region, this thin region denoted by the dashed line in that drawing there, is what we call the boundary layer. It's basically where the velocity goes from the external velocity to meet the no slip condition, decays to zero to meet the no slip condition at the wall. And that region is incredibly thin, right? Just a few centimeters thick on an object the size of 737, right? So it's incredibly thin. And we did it's called the momentum integral estimate to figure out how we can estimate the drag force on, we were just talking about a flat plate, but the drag force on a flat plate if we knew the velocity profile within the boundary layer, right? So the question is, how do we find the velocity profile within the boundary layer? And the thing that we're going to take advantage of is the fact that this boundary layer is so thin, right? So since this boundary layer is so thin, we're going to be able to take the Navier-Stokes equations and through non-dimensionalization and a process called scaling, which is related to non-dimensionalization, we're going to be able to simplify the Navier-Stokes equations. So the basic idea of scaling is that we're going to take advantage of the fact that in this problem, some things are happening in the y direction, and in the y direction, our problem is very thin, right? Our boundary layer is very, very thin in the y direction, right? Delta, the thickness of the boundary layer, is very thin. And other processes, like other derivatives that we're going to take, are going to be in the x direction, right? Other derivatives in Navier-Stokes equations are in the x direction. And the x direction can be pretty long, right? It can be like the length of a 737 or something, right? And so we're going to take our, so the process here of scaling, in the process of scaling, we're going to take our Navier-Stokes equations and instead of just having a single length scale, like we did when we non-dimensionalized Navier-Stokes, we're going to have, in this case, two different length scales. So we're going to have a length scale for x and a length scale for y. So we're going to say that anything that's an x direction we're going to non-dimensionalize by some length L naught, like the length of the plate or the length of the aircraft or something, right? The length of the turbine blade. And everything that's going on in y, all our derivatives with respect to y, we're going to scale or non-dimensionalize by delta, the thickness of the boundary layer. So, and that delta thickness of the boundary layer is much, much smaller than L naught. And what this is going to do, this is going to give us a much simpler set of equations. Because if we have something that is changing, if we have a derivative with respect to y, like if we have a velocity that's varying with respect to y, if we're looking at the derivative of the x velocity, say, with respect to y, it's changing over such a short distance, 5 centimeters on something that's the size of a 737, right? It's changing over such a short distance. So over 5 centimeters, the velocity is going from 0 at the wall to whatever the free stream velocity is flowing past that jet, right? So there's an extraordinarily high gradient in velocity as we move away from the wall. So that means that extraordinarily high gradient in velocity as we move away from the wall is much, much larger than any gradient in velocity that's along the length of the plate or along the length of the aircraft. That's what we get from scaling. So we're going to end up basically keeping all of the derivatives with respect to y and getting rid of all the derivatives with respect to x, and that's how we're going to simplify the Navier-Stokes equations. Yeah.
So with scaling with the boundary layer thickness, the boundary layer thickness isn't constant, like so is it still work out okay, or we feel like
yeah, maybe we should call like delta naught or something. So it's like maybe it's the thickness of the boundary layer at the end of the plate or something, or the mean thickness of the boundary layer. So we're using a single, yeah, in this case, that's a good point. Yeah, boundary layer thickness is a function of x. And here we're just going to use a single length scale that's representative, the rough order of magnitude, the scale of the boundary layer thickness. Okay. So again, if we had a flat plate the size of a 737, my L naught would be the length of the plate. My delta would be like 5 centimeters. Okay. Okay, so this is going to end up with a much simpler set of equations, and we're not going to go through the process of scaling. It's a more advanced analysis technique. It's like a grad level analysis technique, but we will see that we will look at the result. So if we have a 2D steady state Navier-Stokes momentum equation, ignoring gravity, right? So this is what that would look like. So this is now in 2 dimensions. So we're assuming that any plate that we have is like infinitely wide, right? So we're dropping out the Z components. And we've written this, so we're gonna put the, just to give you a flavor of this, if we look at the viscous shear terms, we're gonna say that all the velocities scale as whatever U is, the free stream velocity. And then if we scale X by L naught, we'll end up with this. If we scale Y by delta, we'll end up with this form. Remember when we non-dimensionalized Navier-Stokes, we just had one L, and so we had U over L squared and U over L squared here. So we have 2 different terms here. And if we note that since L naught is much bigger than delta, then 1 over L naught squared is tiny relative to this thing. So since this term is small, we're going to ignore it. And we're just going to be left with this term here. That's fundamentally what scaling is about. We're going to say that some terms are small and therefore can be ignored, and the other terms are big, and so we're going to keep them around. And so if we follow this through the rest of the 2-dimensional Navier-Stokes equations, this general idea, we end up with, that should be du dx, not du du, plus dv dy is equal to 0. So we keep the same form of continuity that we would always have for 2-dimensional Navier-Stokes. So du dx plus dv dy is equal to 0. And the x component of the Navier-Stokes equation simplifies to this. U du dx plus v du dy is u du dx plus 1 over rho d tau dy. This u, this is the free stream velocity. So this is the velocity at the exterior of the boundary layer. And so what we're saying is that there is some dependence on what's happening within the boundary layer depends on what's happening outside of the boundary layer. So if we have a flat plate, the velocity is constant going over the top. That's why we talk about flat plates a lot, because the velocity u outside the boundary layer is big U, capital U, outside the boundary layer is constant over a flat plate. But if we have something like an airfoil, we have some kind of a curved shape, it will change the velocity outside the boundary layer as we move down with x, and so this term is important in that case. And then this is the shear stress within the boundary layer, and in the boundary layer equations for laminar, we end up with mu partial u partial y, and for turbulent flow, we have mu partial u partial y minus this this component of the turbulent stresses, rho times the mean time mean of u prime and v prime. So this has gotten far simpler than what we had in the than the full 2-dimensional Navier-Stokes. So we've dropped out a whole bunch of different terms here, and so this is now amenable to more analysis. Like we can actually do something with this. Yeah. So this is the variation of the external velocity capital U along the outside of the boundary layer. So these are called the boundary layer equations, right? So this is a form of the Navier-Stokes equations that describes what's happening within a boundary layer. So they're much easier to solve than the full Navier-Stokes equations. Many interesting and useful solutions exist. I think those are the words of your textbook. Interesting and useful solutions. So if you're looking for something interesting to read at night or something, you can read about the boundary layer solutions. We're going to talk about one. One especially important solution is for the flat plate boundary layer. So this was developed by Blasius in 1908, and it's for a flat plate boundary layer, so a boundary layer with a constant velocity in the free stream, right? So that capital U is a constant, right? So we're not going to have any turbulent stresses. We're going to consider just the case for laminar flow. And this is a problem, right? We consider it an analytical solution, even to some explicit function of y. This solution is actually in terms of an ordinary differential equation. So you still have to integrate it numerically in order to write out or in order to evaluate the velocity profile, but nonetheless, we consider this solved or analytical. This is what that solution looks like. It's in terms of the x direction velocity u and the y direction velocity v, plotted here as a function of distance from the wall. And we can see this, this fairly smooth rise in velocity as we move away from the wall, or the smooth rise in velocity as you move away from the wall. That's plotted here. We'll look at an experimental visualization of this to make a little bit more physical sense on the next slide. But once we have the velocity profile, then we can basically take, just like once we had the analytical solution for laminar flow, for internal, for pipe flow, we could then ask questions. We can then take that solution and solve for all of the different parameters, all of the different features of the flow that we were interested in. We can do the same thing here. So one of the things that we discussed was how thick is the boundary layer, what is delta? Well, so with this, with the solution from Blasius, we can then develop an expression for the thickness of the boundary layer. So one way to define it is where the velocity in the x direction is 99% of the way to the free stream velocity. So this thing continuously decays, right? Continuously asymptotically approaches the free stream velocity. So we can never, the solution never goes to exactly u is equal to, little u is equal to big U. So we're just going to take, in this case, the point where it's 99% of the way there and say that's our boundary layer thickness. That's one way to define the boundary layer thickness. We'll look at a few others. And then we end up with delta over x is 5 over Reynolds number over the square root of Reynolds number based on x. So x appears on both sides, okay? And then we can see that the thickness of the boundary layer is a function of x, and that's captured by this expression. Okay, yeah. Yeah. Yeah, we're gonna see that on the next slide, I believe. Yeah. Sorry. So from this we get the boundary layer thickness. So we can solve for the wall shear. So the wall shear is that tau wall. So we get tau wall as a function of x, evaluates to this expression here. And now if we plug that in, we can find, and we'll end up with the coefficient of friction for a flat plate, 0.664 over the square root of REX. So we call this the skin friction coefficient when we're talking about flow over a surface like this. So CF, we're going to look at that for turbulent flow as well. And this skin friction coefficient, just want to note, this skin friction coefficient is a function of x. So this is like the drag force per unit length along one short section of the plate, right at one particular location on the plate. Since the boundary layer is growing and changing, right, growing as we move downstream, the force the drag force at every point on the plate is also changing, right, as we move downstream. This skin friction coefficient is a function of X. But when we have a real experiment, if we have a real flat plate, then we want to know the total drag force that plate experiences. We could basically just take this thing and integrate it along the length of the plate. What we end up with is the drag coefficient CD, which evaluates this 1.328 over square root of RE based on L, the Reynolds number based on plate length. This then we could plug into the formula that we showed last time for drag force, and evaluate this to find, use this to, for example, to find the drag force on a plate of length L. I want to talk for a second about boundary layer thickness, because boundary layer thickness is a little bit hard to define. The laminar case, so this is now an experimental visualization, which I think is a little bit more intuitive than what we saw on the previous slide. We can see that, so this visualization was generated by basically releasing a little bit of either smoke or probably bubbles from this wire at some time, and then a photograph was taken, some very short time later, and you can to visualize how far those bubbles had traveled downstream. And what you can see then is kind of a shadow of how far those bubbles had made it. And we can see this shape here, right, that's curving up. So normally we would draw this with arrows indicating what the velocity profile looks like, right? So if we were to imagine drawing in arrows, in fact, maybe I have that on this slide. Yeah. This shows us the velocity profile experiment in a laminar boundary layer, right? So we can see it smoothly moving up to whatever the free stream velocity is. Yeah. What's confusion? Oh, sorry. Okay. Okay. What did you just get? Because somebody else might be stuck with it. So it is displacement of the fluid, right? But it's displacement of the fluid over a fixed time. Okay, got it. Yeah, so we take this image a short time after we put the bubbles into the flow, and then we can see how far those particles traveled, right? This is like delta x over delta t, and so it's a measure of velocity. Okay. Yeah. Okay, so any questions, any confusion on that? Okay. So it's a visualization of velocity, but we can see that there's a constant decay to the free stream velocity u. So how do we define thickness, right? We could go in, which would give us a thickness, right? A delta of this, right? We could say it's 99% of the way there. That's the expression that we looked at on the previous slide. And that's actually very different, right? Because the slope of this decay flattens out quite a bit. We could come up with say it's 0.999 U or something else, right? Or say that 90% of the way there, or 2/3 of the way there, or something is fine. I mean, there are many different ways you can come up with to try to define boundary layer thickness, and so consequently, there are many different definitions of boundary layer thickness. There's no one uniform number or no one uniform equation that we would use to capture exactly what the boundary layer thickness is. Yeah.
Exactly this in a logical way. If the Reynolds number decreases, like as the Reynolds number decreases, is the ratio of the boundary layer thickness to the length of plate or penetrate whatever we're talking about, that ratio increase, so it becomes more significant. Like, we're looking at 5.9.
Ratio of, I guess maybe I'm not fully understanding. I'm not fully understanding what you're asking. Sorry.
Like, as the rental number goes down.
Yeah.
Does basically the boundary layer thickness increase? And so it's more.
So delta over delta over X goes as 1 over square root of Reynolds number, right? Goes as Reynolds number to the -1/2. So it gets smaller. Reynolds number goes down. Sorry, as the Reynolds number goes down, it gets thicker, right? The delta over X gets higher, gets bigger. But the difference between, and so the difference between these two would become more significant, but not in non-dimensional form. So this, okay, I'll say this profile has the same shape. For a laminar boundary layer, it always has this shape, no matter where we are on the plate. As long as we're in the laminar flow regime, we're going to talk about transition to turbulence. But as long as we're in laminar flow, it always has this shape. It's just a matter of how much we scale this shape by, right? So for example, as we move down the plate, the velocity always has this profile. It's just that when the boundary layer is really thin, this profile is, when the boundary layer is really thin, this profile is really small, right? And as it grows, to move down the plate, it always has this shape. So as REX goes up, the boundary layer thickness increases. As REX goes up, the boundary layer thickness has to increase. But the so let's just go back to the formula there for a second, because I see some confusion. So boundary layer thickness, if we take the 99% definition, your delta over X is 5 over square root of REX. So we could write this out as 5 times mu over, just write that out. So delta 99 over X is 5.0 over square root of REX, right? So that's 5 mu over square root of mu over square root of rho UX. But now we're going to take this X to figure out what the actual thickness of the boundary layer is. We're going to say that delta 90, take that X and multiply it through. We'll end up with delta 99 is 5 square root of mu X over square root of rho U. So as X increases, the boundary layer thickness increases. So as we move downstream, the boundary layer thickness increases. Yes. Have I made things better or just confused? I forget what the initial question was. Sorry, did I make things better or worse? Okay. But I saw some confusion though when I mentioned that boundary layer thickness increases. Like this expression tells us that the boundary layer thickness increases as we move downstream. And that's because the X appears on both sides. Okay, so when we resolve it though, we see that it does in fact increase as we move downstream. Okay. And we would call it self-similar because it always has the same shape, right? It's always the same shape. It's just scaled as we move downstream. So this 99% saying that the boundary layer thickness is where the velocity is 99% of the free stream. It's a little bit imprecise. And so there are other sort of more precise ways of defining boundary layer thickness. So one is what's called the displacement thickness. It's defined as, so it'll be written as like this delta star, and it's the integral, through the whole boundary layer of 1 minus little u over big U dy. this actually comes from it comes from our momentum integral estimate. This was one of the terms that appeared in our momentum integral estimate when we were looking at that on Monday. It's basically a measure of like how far. So we talked about how this outer streamline gets displaced because the fluid is being slowed down by the wall. And by mass conservation, if we have a certain amount of mass coming in here at uniform velocity, and then that flow is slowed down, right? In this case, it's slowed down by the plate, the area has to increase. And so this streamline here has to deflect upwards. The displacement thickness is a measure of basically how far this streamline deflected upwards. That would be the displacement thickness. This del star is for a laminar boundary layer is about 1/3 of delta 99. But it has a nice definite form. Sometimes another expression that's used is the momentum thickness. This would sometimes written as theta. Similarly, it's an integral over the whole boundary layer or over the whole solution to the boundary layer. U over U, little u over big U times 1 minus little u over big U dy. With this definition, we end up with the momentum thickness expression. So momentum thickness over x is 0.664 over square root of Reynolds number. So and then another thing that's another factor that's used to describe the boundary layer thickness or the shape of the boundary layer rather is what's called the shape factor. So it's basically just the ratio of these two things. So delta star over theta. Yeah. Yeah. So yeah, it's a little bit confusing, right? Because we have delta here. So for the this would be where the velocity truly is equal to the free stream velocity. So for the laminar boundary layer solution, we can take this as infinity, and we could actually evaluate this all the way out to infinity. And this thing still has a finite form, even though we take the limit at infinity.
Could you say 21%? What was the capital?
So capital D is our drag force. So this, so where this theta comes from is that this theta, if we know what the momentum thickness of the boundary layer is, then we can just plug that in to figure out what the drag force on the plate is. Yeah, sorry. So that's showing more or less like this comes out of the. So if we went back to the momentum integral estimate that we did on Monday, we saw that we said that the drag force D was rho B times capital U squared times this integral, right? So if we just say that that integral is going to be our boundary layer thickness, we're going to call it the momentum thickness theta, then we can write the drag force in terms of that momentum thickness theta. For laminar flow, we end up with this expression for the momentum thickness theta, 0.664 over square root of Reynolds number. Yeah, so then another way that we can characterize the boundary layer is by the ratio of these two things, which is called the shape factor. So it's delta star over theta. Confused? Lowercase. Oh, yeah, sorry. This is the width of the plate. Yeah. So we're assuming the width of the plate is much, much larger than our length or something, right? So we're ignoring changes in that, over that dimension. Yep. It is. Yeah. So all of these things are dimensionless. Yes. Actually, no, sorry. This is not dimensionless. Sorry, this is not dimensionless. Yeah. Yeah, I know we do we were using this to indicate dimensionless form, so that is a little bit confusing, but this is not dimensionless. How do I know that this is not dimensionless? This has dimension of length. Yep. Now, I mean, we could have defined this in a dimensionless form, so that doesn't quite tell us, but if you know that this has dimensions of length, then you know that this also has dimensions of length. So another way we can look here. Yep. Yep. So if we do a dimensional analysis of this equation, right, we're going to get exactly there. So 1, this is dimensionless. Little u over big U, this is dimensionless. This whole term here is dimensionless. But it's integrated with respect to dy, and there's no other factor. We're not dividing by a factor of length or something. And so this is a dimensional form of the equation. Yeah. Okay. Shape factor is dimensionless. So it's the ratio of 2 lengths. So H is dimensionless. For a laminar boundary layer over with a on top of a flat plate, the shape factor is about 2.59. What we're going to see when we discuss turbulent boundary layers is that the shape factor is only about 1.3. What the shape factor tells us is how likely separation is to occur. So how likely the boundary layer is to separate from the object. We'll see this in the context of like flow around round objects, for example. We previously saw a visualization of flow around a sphere, and said that the limitation of our boundary layer analysis is that it fails when the boundary layer is no longer close or no longer remains close to the object. That's called separation. And this is telling us the shape factor basically is our first hint that laminar boundary layers are more likely to separate than turbulent boundary layers. Okay. I just want to return to this question of why transitional Reynolds number in internal flow is different from transitional Reynolds number in external flow, now that we've discussed boundary layers a little bit. So another answer, so the initial answer that we gave was that D is measured across the flow and L is measured along the flow. And since those measurements, the length scale, are in different directions relative to the flow, we end up with different transitional numbers, Reynolds numbers, right? That's what we gave as the explanation last chapter. But that's still kind of like it's this way because I told you it's this way explanation. So I don't find that satisfying. So another answer is that the thing that really controls the transition to turbulence is the thickness of the boundary layer. The thickness of the boundary layer is what determines the transition to turbulence. And boundary layers are typically thin, meaning that the thickness of the boundary layer is small relative to the length of the object. In internal flows, we typically assume that the boundary layers are merged, meaning that the diameter of, right, because we assume the flow is fully developed. If we come back to this drawing that we looked at the beginning of the internal flow chapter, we showed these dashed lines, like, growing as we move down the pipe. Those dashed lines, they actually represent boundary layers, right? And what we're looking at here is the growth of the boundary layer on the inside of the pipe as we move down, as we move with respect to X. But we said in last chapter, we said we're going to just really consider only what happens in the fully developed region after, right? And at that point, those two boundary layers have met one another. And we're only concerned with what happens downstream of that for internal flow. And so that means that the diameter that we use is basically the boundary layer thickness in internal flow. The boundary layer can't grow any further. Once they've merged, they can't grow any further. And so the diameter of the pipe, or is the radius of the pipe, but that's close to diameter, is about the thickness of the boundary layer. And so when we write transition, when we look at transition in internal flow based on RED, we're defining transition based on the thickness of the boundary layer. Transition to turbulence based on thickness of the boundary layer. But in external flows, there's nothing for the boundary layer to meet. Right? We've seen that even defining the thickness of the boundary layer is a little bit tricky, right? So we just use the length of the object as our scale, right? So we use RE sub L. But since the length is much, much greater than the boundary layer thickness, our transitional Reynolds number, our transition to turbulence, our Reynolds number for transition to turbulence in external flow is substantially higher. Okay, so typically on the order of 500,000. So so transitional Reynolds number is different for internal versus external flow, even though turbulence for internal flow and external flow are basically the same. It's the same fundamental process. The transitional Reynolds numbers are different because we measure it differently, right? One is across the flow, one is down the flow. The reason we get different answers is because boundary layers are thin. Does that make some sense? Okay, main thing to take away is that there are different transitional Reynolds numbers for internal and external flow. And we can get some understanding of it by looking at boundary layer theory. So these are some visualizations from Album of Fluid Motion. So for example, this is a flat plate at Reynolds number of 10,000, right? So Reynolds number based on length of 10,000. So if this were Reynolds number based on diameter of 10,000, we would be definitely in the turbulent regime, right? But we actually see this is a nicely laminar profile. And for Reynolds number 15,000 for flow around this sphere, the flow is actually laminar up to the point where it separates, and there the boundary layer becomes incredibly thick, and we start having a wake which decays into turbulence. But the boundary layer itself is entirely laminar, even though our Reynolds number is 15,000. So we would define both of those as laminar flows, even though the Reynolds number is in the tens of thousands, because of this difference. Okay, any questions on that? All right, so I want to start talking about the transition to turbulence. So we've talked about laminar flow. We kind of ignored the question of transition. We talked a little bit about it in videos last chapter. But for the most part, we said, like, there be dragons, right, in the transitional Reynolds number regime. And so we're going to try to avoid it, but we can't in external flows. So so that transitional Reynolds number for transition to turbulence in external flows, it can be delayed to a Reynolds number based on length of up to 3 million. But in order to do this, you need a surface that is polished smooth, like near perfectly smooth, and a perfectly calm free stream. So no gusts, no disturbances, no trucks driving by outside causing vibrations in the floor that move the thing around. So that's like the absolute upper limit of where it's been, where laminar flow has been demonstrated through. So this is difficult to achieve in practice, right? Those conditions don't really exist in the real world. So we typically say that a transitional Reynolds number of about 5 times 10 to the 5th, that's more typical, right? But even before the flow is fully turbulent, there's a transitional regime that starts somewhere around 100,000 Reynolds number based on length of about 100,000. And in that transitional regime, so we'll define it as about 100,000 to about 1 million. So if we have a Reynolds number based on length somewhere in this range, we're going to say that the flow is transitional, meaning that it is neither, by the end of the plate, by the end of the object, it is neither fully turbulent nor fully laminar anymore. This transition plays a significant role in what's going on in the flow. So this is for Reynolds number based on length of about 10,000, so firmly within the laminar flow regime. We have, so it's a visualization of flow over a flat plate. We see nice smooth streamlines as we move towards the back of the plate, indicating we have nice laminar flow. Whereas as we get up to 100,000, so this is below our 500,000 sort of working cutoff, right? but we can see that we're starting to get this kind of wavy behavior. Some weird things are happening at the edges. This flow is transitioning from laminar to turbulence, right? Which would happen if we made the plate longer or if we accelerated the flow a little bit more. And so this is fundamentally different than this. This is also fundamentally different than turbulent flow, right? Than full turbulent flow. It's kind of its own thing. And so we're going to call it transitional flow. Turbulence doesn't just start all at once. It's not like we just reach. So as we move down the plate, Reynolds number based on X is increasing. Our boundary layer is increasing in thickness. And at some point we go from laminar into this transitional regime into a turbulent regime as we move further and further down the plate. But that turbulence, it's not like we get to some point and all of a sudden it's turbulent. In this transition region, sort of as implied by the name, that's where the turbulence kind of begins to form. And typically what's observed are what are called turbulent spots that have this kind of like arrowhead shape that just appear, and we'll see a visualization of this on Friday, and appear randomly and then grow as they move downstream. And so we'll see a video of this happening, but this is what they look like. And here we can see visualization of these turbulent spots at different Reynolds numbers from 100,000 to 400,000, all have basically the same shape, but they just kind of appear within the flow, or they appear as if they just emerge all of a sudden. And what we'll see, just to set this up, is that what the flow then looks like is that you have this kind of like sea of laminar flow with these little islands of turbulence. These little islands of turbulence move downstream and grow until they eventually merge, and then you have fully turbulent flow on the other side. And so we'll see a video of these things forming, moving downstream, growing as they move downstream, and eventually they grow so much that they all merge together, and we end up with fully turbulent flow. This is what that looks like from the top. From the side, this is what it actually looks like. So it has some kind of a shape to it. And they all look pretty similar. These turbulent spots all look pretty similar to one another. This is another drawing of what the transition to turbulence looks like. You can see there'll be kind of waves, that waviness that we saw in one of those visualizations, and those waves kind of deform and change shape until at some point we start getting these turbulent spots appearing and moving downstream. So here's another visualization of it. So this is what's plotted here is thickness, boundary layer thickness is a function of X. So this is a laminar regime. It's defined by what we talked about previously. This is the turbulent regime. We're going to talk about a form of what the boundary layer thickness looks like down here. And this is the transitional regime, where we don't have as good of a form for what this boundary layer thickness is. Nonetheless, we'll use experiment to try to understand it. One final note, I guess actually we'll call it there. So we'll talk about separation in turbulent flow, probably by way of video, and then we'll get into this on Friday. And this is where we'll pick up then. All right, thank you all. See you on Friday.